Bismillahirrahmanirrahim. Assalamu alaikum. I'm Dr. Faidullah and you are watching Easy Mathematics. In this video, we shall present an introduction to ordinary differential equations. These are the topics which we shall study in this lecture. Let us start from the first one. Let us see the definition of a differential equation. We say that an equation containing the derivatives of dependent variable with respect to one or more than one independent variable is called a differential equation. There are two types of differential equations: ordinary differential equations and partial differential equations. We say then that an equation involving the ordinary derivatives of a dependent variable with respect to a single independent variable is called an ordinary differential equation. And an equation containing the partial derivatives of a dependent variable with respect to more than one independent variable is called a partial differential equation. Let us see some examples. In the first example, we have dy by dx plus y equal to 0. This is an ordinary differential equation because it involves the ordinary derivatives of a dependent variable y with respect to an independent variable x. Let us see another equation: dy over dx plus y cos x is equal to sin x. And we can see this equation involves the ordinary derivatives of a dependent variable y with respect to an independent variable x. So this is an ordinary differential equation. Let us see another example. In this example, we have del u over del x is equal to del v over del y. This differential equation involves partial derivatives of dependent variable u and v with respect to independent variable x and y. So this is partial differential equation. Let us see another example: del square u over del x square plus del square v over del y square is equal to 0. We can see this equation involves partial derivatives of u with respect to x and v with respect to y, and this is second order differential equation. So this is a partial differential equation. Order of a differential equation. The order of the highest derivative occurs in the equation is called order of a differential equation. Degree of a differential equation. The greatest power of the highest order derivative occurs in the equation is called degree of a differential equation. Let us see some examples. Now, in this first example, we can see that the highest order derivative is d square y over dx square. So its order is 2. Order of this differential equation is 2. And the power of the highest order derivative that appears in the equation is called its degree. So we can see the power of the highest order derivative is 3. So degree of this differential equation is 3. Now look at example number 2. In this example, the highest order derivative is 2. So we can say order of this differential equation is 2. And power of the highest order derivative in this equation is 1. So its degree is 1. Now look at example number 3. Before to find order and degree of this differential equation, we have to finish this fraction. Let us square both sides. So after squaring both sides, we get 1 plus dy over dx whole square whole power 3 is equal to d cube y over dx cube whole square. Now we can find degree and order of this differential equation. So order of this differential equation is the highest order derivative. So the highest, this is first order derivative and this is third order derivative. So the highest order of the derivative in this equation is 3. So order of this differential equation is 3. Now degree of this differential equation. So the power of the highest order derivative. So the highest order derivative is d cube y over dx cube and its power is 2. So degree of this differential equation is 2. Linear ordinary differential equation. Let us start from the definition. We say that an ordinary differential equation g of x comma y dy by dx up to nth derivative of y with respect to x equal to 0 is a linear ordinary differential equation. If the function g is linear in x, y, dy by dx up to dny over dx power n. A general linear ordinary differential equation is an equation of the form 1, which is a n of x, nth derivative of y, plus a n minus 1 of x, n minus 1th derivative of y, plus up to a naught of xy minus f of x equal to 0. Now, if the function f of x is 0, then it is known as a homogeneous ODE. And if the function f of x is not equal to 0, then it is called a non-homogeneous ordinary differential equation. Let us see some example. Dy over dx plus y is equal to x. This is a linear ordinary differential equation. Here f of x is x. Now the coefficient of dy over dx, it may be a function of x or some constant, let us say 2. Then again this is a linear ordinary differential equation. Let us write another definition. X d square y over dx square plus dy over dx plus 3y is equal to e power x. This is an ordinary differential equation which is linear because the coefficients of all d square y over dx square, dy over dx, similarly y, they are function of x. and f of x in this case is e power x. Now if e power x is 0, this is homogeneous. But now it is a non-homogeneous ODE because we have a function e power x. Similarly, from equation 1, if I write d2 dy over dx plus y equal to 0, now this one is homogeneous, but the star, that one is a non-homogeneous because f of x is x in star. Now let us write another equation, dy over dx plus sine x y is equal to cos x. This is a non-homogeneous ODE because f of x in this case is cos x. To classify the linear and non-linear ordinary differential equations, let us see the key points. We will say that an ordinary differential equation is linear if it satisfies three conditions. Number one, the dependent variable y and its derivatives are all of degree 1. Number two, there will be no product of y and or any of its derivatives. Number three, there will be no transcendental function of y and or its derivatives. By transcendental functions, we mean trigonometric functions like sine y, cos y, tangent y, exponential function, e power y, 2 power y, logarithmic function, ln y, and so on. If any one or more than one of these conditions are not satisfied, then the ODE is called a nonlinear ODE. Let us see some examples. In the first example, we have dy over dx plus y square is equal to 2. This is a non-linear ODE because of y square, because the degree of y is 2. Let us see another example. 2 dy by dx plus sine y is equal to e power x. This is a non-linear ODE because of sine y, which is a transcendental function. Number 3, y dy by dx plus y is equal to e power x. This is a non-linear ODE because of the product y and dy over dx. What is solution of an ordinary differential equation? Let us see the definition. A relation between the dependent and independent variables is called a solution if it satisfies the following two conditions. Number one, it does not contain derivatives. Number two, this relation and the derivatives obtained from it satisfy the given ordinary differential equation. Let us explain it by an example. In this example, we have an ordinary differential equation d square y over dx square plus y is equal to 0. Its solution is y is equal to a sine x plus b cos x. Let us say this is 2. If we say that 2 is a solution of ODE 1, it must satisfy the above definition. We can see this is a relation between y and x, and it is free from derivatives. There is no derivative. So condition 1 is satisfied. To show that condition 2 is true, let us differentiate 2 with respect to x. We have dy over dx is equal to a cos x minus b sin x. Let us differentiate it once again. D square y over dx square is equal to minus a sin x minus b cos x. Let us take minus as common. We have a sin x plus b cos x. Now from 2 we can see that a sin x plus b cos x is equal to y. So therefore we can get d square y over dx square is equal to minus y from 2. Now if we simplify this, we have d square y over dx square plus y is equal to 0. And hence we can see that the relation 2 and the derivatives obtained from it satisfy the given ordinary differential equation. Hence 2 is a solution of ODE 1. Later on, we shall learn how to obtain a solution of ordinary differential equation. Initial and boundary conditions. In this course, later on, we shall study different methods to solve ordinary differential equations. We will see that we use integration techniques to solve ODEs, and hence integration constants appear in many places. Due to integration constants, solutions to ordinary differential equations are usually not unique. To get the value of integration constant, we use two types of conditions with ODEs, and they are called initial conditions and boundary conditions. Let us start from the first one. Initial conditions. If the conditions with ordinary differential equations are given at only one value of the independent variable, then those conditions are called initial conditions. We usually write it as y of x naught is equal to y naught. So there is only one value x naught of the independent variable. Let us explain it by some example. In example number 1, we have a problem. Solve the ordinary differential equation dy by dx is equal to 2x such that y of 1 is equal to 4. In this problem, we have a condition. The condition is given at only one value x naught is equal to 1 of the independent variable. So this condition is an initial condition. Let us see another example. In this example, we have a problem. Solve d square y over dx square plus y is equal to 0. Subject to the conditions y of pi by 4 is equal to under root 2 and y dash of pi by 4 is equal to 1 over under root 2. Now we can see that there is only one value of the independent variable. X naught is equal to pi by 4. So these conditions are called initial conditions. Now let us explain what are boundary value conditions. If the conditions with ordinary differential equation are given at two or more than two independent variables, then those conditions are called boundary conditions. We usually write y of x naught is equal to y naught and y of x1 is equal to y1. So we will see that there will be two or more than two values of the independent variable. Let us explain it by some examples. In this example, we have a problem. Solve the ordinary differential equation d square y over dx square plus y is equal to 0 with the given conditions y of 0 is equal to 1 and y of pi by 2 is equal to 2. Now we can see that there are two values of the independent variable. In this case, x naught is equal to 0 and x1 is equal to pi by 2. So this is a boundary value problem and the conditions are boundary conditions. Let us see another example. In this example, we have solve d square y over dx square plus y is equal to 0. Subject to the initial condition or boundary condition, which we will see that which type of conditions are given, y of 0 is equal to 1 and y of pi is equal to 5. Now we can understand that whether they are initial condition or boundary condition, because here the value of x naught is 0 and the value of x1 is pi. So conditions are given at two values of the independent variable. So these are boundary conditions.